Hi, I am Mark A. Barayoga, your reporter this afternoon, and today I am going to discuss about kurtosis. At the end of this video, you are going to learn three things.
The definition of kurtosis, three types of kurtosis, and how to compute for kurtosis. Like skewness, kurtosis is an statistical measure used to describe the degree to which scores cluster in a tail or a peak of distribution. The peak is the tallest part of a distribution, and the tails are the end of the distribution.
Basically, kurtosis is a way of presenting our data. If we have learned in the past lessons that we can use line graph to show a trend, or a pie chart to show how each part is divided according to its percentage, and many others, well, kurtosis is telling us how our data is distributed and if it contains any outliers. Outliers are extreme values that make our dataset abnormal.
Three types of kurtosis.
There are three types of kurtosis. We have the mesokurtic distribution, the leptokurtic distribution, and the platykurtic distribution.
The first type of kurtosis is mesokurtic. Mesokurtic distribution is neither high nor low. It is the baseline for the two other classifications. It has a kurtosis of 3 just like a normal distribution. It does not contain outliers. Second is leptokurtic. Leptokurtic distribution has a high peak and a slender tails. It has a kurtosis of more than 3 because it contains outliers. And lastly, platykurtic. It has the lowest peak. It indicates that the distribution is flat and has a kurtosis less than 3. It contains no outliers. To compare the kurtosis that you have to that of a normal distribution, we just have to get the excess kurtosis. Excess kurtosis is equals to kurtosis minus 3. For example, you found out that the kurtosis of your dataset is 5. Just subtract 3 to 5. Then, you have a positive 2 excess kurtosis. When you obtained a positive excess kurtosis, it means that your dataset will have a leptokurtic distribution. To iterate it once more, mesokurtic distribution has an excess kurtosis equal to 0. Leptokurtic distribution has a positive excess kurtosis, and the platykurtic distribution has a negative excess kurtosis. Kurtosis isn't just a theory confined to mathematical textbooks. It has a real-life applications, especially in economics such as in risk management. In investment returns, platykurtic distributions, or those with negative excess kurtosis, generally produce results that won't be very extreme, which are great for investors who don't want to take a lot of risk. How to compute for kurtosis?
To get the kurtosis, we should first get the mean and the standard deviation, which was discussed already on the past lessons. If you don't know yet how to get the mean and the standard deviation, I highly encourage to review those first.
First step is to get the mean. If you want to get the population mean, we have the formula. Population mean, or that symbol, which is called mu, is equals to sum of all data over n. For sample mean, we have the formula sample mean, or that symbol, which is called x bar, is equals to sum of all data over n. After you get the mean, the second step is to find the standard deviation. If you want to get the population standard deviation, we have the formula. Population standard deviation, or that symbol, which is called lowercase sigma, is equals to the square root of the summation of x minus population mean raised to the second power all over n. And if you want to get the sample standard deviation, we have the formula. SD is equals to the square root of the summation of the quantity of x minus sample mean raised to the second power all over n minus 1. Now that you have the mean and the standard deviation, we are all set to get the kurtosis. If you want to get the kurtosis of a population data, we have the formula. Kurt is equals to the summation of x minus population mean raised to the fourth power all over n times population standard deviation raised to 4. And if you want to get the kurtosis of a sample data, we have the formula. Kurt is equals to the summation of x minus sample mean raised to the fourth power all over n minus 1 times the standard deviation raised to 4. As you can observe, we are always given with two formulas, one for population data and one for sample data. But what is the difference between the two? For example, you want to survey a community. One of the questions says, if the election is to be held tomorrow, who will you vote as president? The community has 1 million people, and let us assume that all of that 1 million people are of voting age. If you will be surveying individually the 1 million people, then you are using the population data. But when you only opted to survey 1,000 people out of the 1 million people, then you are using the sample data. It is very important to give an emphasis about the difference of these two so that we will be constant with the formula we will be using. If we opted to use the population data, then we will be getting the mean, the standard deviation, and the kurtosis of a population data. Mr. De La Cruz is a professor teaching in Intro to Statistics course. At the end of the semester, he has all of his 20 students completed a final exam consisting of 100 multiple choice questions. The scores that his students received are as follows: 80, 75, 85, 80, 100, 90, 95, 80, 85, 90, 90, 90, 95, 90, 95, 80, 75, 90, 70, and 90. From this problem, we can already say that the test scores of his students are ungrouped data. We will be using the population data to get for the mean, the standard deviation, and the kurtosis. Let us arrange the data to ascending order. Then, we are going to get the summation, or simply, we will add all of the data. The sum of all the data is 1,725. To get the population mean, we have the formula. Population mean is equals to sum of all data over n. The sum of all the data is 1,725 and n is 20. The population mean is 86.25. Now that we have the mean, we need to find the standard deviation. We have to draw a second column beside x. We will label it as x minus population mean. The data that we have on the first column, which is labeled x, will be subtracted to our population mean, which is 86.25. Now, we have the difference between the x and the population mean. Next, we are going to draw another column. We will label it as x minus population mean raised to the second power. Basically, we will just raise to the second power the difference that we obtained on the second column. We are going to get the summation of all the data in the third column. The sum is 1193.75. Then, we can compute for the standard deviation. We have the formula. Population standard deviation is equals to the square root of the summation of x minus population mean raised to the second power all over n. We just have to substitute all of the data that are given already. Our population standard deviation is 7.73. To compute for the kurtosis, we have to draw the fourth and last column. We will label it as x minus population mean raised to the fourth power. Basically, we just have to raise to the fourth power the difference that we have obtained on the second column. Then, we are going to get the summation, or simply, we will add all of the data in the fourth column. The sum of all the data in the fourth column is 162,587.89. Now, we are all set to get the kurtosis. The formula in getting the kurtosis of a population data is Kurt is equals to the summation of x minus population mean raised to the fourth power all over n multiplied to the standard deviation raised to 4. The kurtosis is 2.27. Lastly, we are going to get the excess kurtosis. We have 2.27 minus 3. It is going to give us negative 0.73. That means we have a negative excess kurtosis. The kurtosis of the 20 test scores of Mr. De La Cruz in his subject Intro to Statistics is negative or platykurtic.
Thank you very much for watching this report. I hope you learned a lot. If there is something that you missed, feel free to rewatch again this video. Stay safe and God bless.